Chapter 5. We're working on trigonometric identities basically for the entire chapter. And we are up to 5.4. So in 5.3, we looked at sum and difference identities for the cosine function. And so what we can see here in in section 4, we are also going to look at sum and difference identities, but now for the sine function. And then since we're getting used to these things, we're going to throw them in and also look at them for the tangent function. And after that, we basically want to apply them. So the idea here, like in the last section, is that we are going to be given an identity for the formula basically for a sum or difference of angles in initially the sine function here, as we did in cosine in the last section. And then we're going to look at how we can apply that identity to rework things or rewrite things in different ways. So this will go along a similar path. Obviously, the formula for sine will be a little different than the formula for cosine, but actually they look very similar. So let's take a look here. So it says we can use the cosine sum and difference identity to derive similar identities for sine and tangent. So instead of trying to justify these from scratch like they did for cosine, we can now lean on the cosine one instead, because as we've learned before with the cofunction identities, we can convert sine to cosine and vice versa. So they begin by saying, all right, let's say we wanted to look at the sine of a sum of angles. Well, using the cofunction identity, we can convert that to 90 minus that sum of angles. And then with a little bit of algebra playing around and then using the cosine difference of angles formula, they end up with this result. And so we could, I think they might have a summary for us a little later, but we end up having that the sine of A plus B is sine A cosine B plus cosine A sine B. And when we have the cosine formula before, we had kind of a similar pattern, but instead of having sine and cosine in each, it had cosine cosine minus sine sine, where here we have sine cosine plus cosine sine. And so there's a sort of an oddly slightly different pattern, but you end up being able to sort of know that they basically all look very similar. And that way you kind of are able to use them more quickly and easily when you get used to them and spot them when you need to use them in different kinds of problems. But anyway, so here's a result. And then similarly, if we were looking at the difference, we would come up with a similar result. And in the case of the cosine sum, you may recall that when you had a sum with the cosine, you had a difference. Now, when you have a sum with the sine, you have a sum with this pattern of sine, cosine, cosine, sine. And then when you have a difference, you then have a difference with the same pattern, sine, cosine, cosine, sine. So written this way, we're hopefully going to make it a little bit easier to commit it to memory. If you use it, after a while, you'll start to remember what the theorem says. But again, in our case, you can always look it up if you need to. So here is the little summary. And we can try to see the pattern here. And you can imagine applying that to a different difference or sum of angles as we did before. So I did sort of my own example here last time, but let's look at their first example. Well, before they do an example of the sines, they move on to the tangent. So I guess I will do an example here because I think it's a little nicer when we first see these to look at an example. So let's say I was trying to find the sine of, similar to what we did before, we were able to do like 15 degrees when we had the cosine. And we could recognize that 15 degrees is 45 degrees, which is an angle we know for the sine function, and for cosine, minus 30 degrees, also an angle that we know. And if I take that difference, I get 15 degrees. And so I could then write sine of 15 degrees to be equal to the sine of 45 degrees minus 30 degrees. And then use the formula right above, where A is equal to 45 and B is equal to 30. So then this identity would tell me I can take this sign of this difference by doing sine of A, which is 45 degrees, times cosine of B, which is 30 degrees, minus cosine of 45 degrees, times sine of 30 degrees. So we convert sine of 15 degrees into a formula of sine of 45 and 30 because we know those values. And we can now recall, as we do these again and again, sine of 45 degrees is the square root of 2 over 2. And cosine of 45 degrees is also square root of 2 over 2. The cosine of 30 degrees is square root of 3 over 2. And the sine of 30 degrees is 1/2. And by filling in those 4 trig angle values, because we know them all, we can use this arithmetic on the right to give us the exact value for the sine of 15 degrees, which was our goal in the first place. So on the left here, I get root 6 over 4. And on the right, I get root 2 over 4. So in the end, I get the square root of 6 minus the square root of 2 over 4. So here's sort of an initial, not too complicated starting value, similar to what we did with cosine, of how we could use these new sine, sum, or difference formulas. Okay. All right, so now it looks like they're going to do the same thing for tangent. So they begin by saying, if I want to get the tangent of A plus B, I recognize that tangent is sine over cosine. So that's the sine of A plus B over the cosine of A plus B. And we now have formulas for both of those. So I can plug in the formulas for these. And then on the top, I would get the formula for sine A plus B, which we just passed over above. And on the bottom, I would get the cosine. What are they doing? Multiplying numerator and denominator by 1. So they're trying to basically simplify this somewhat. And so they're recognizing that if you multiply the top and the bottom by 1 over cosine A divided by cosine B, then you would distribute that. So just to sort of show you where they're going here, they're trying to make a simplification here. And so then you would distribute this to these two, and you would distribute this to these two. And when you multiply cosine A, cosine B times the first term, the cosine B's would cancel. And on the second term, the cosine A's would cancel. Woohoo! So they're doing the distribution here. So maybe we can see the canceling here. So then in this case, the cosine B's would cancel. Here, the cosine A's would cancel. Here, cosine A's cancel. And cosine B's cancel. And so this allows us to recognize in the top, you have sine A cosine A. And then the other fraction is sine B over cosine B. And same patterns in the bottom. And then we can end up writing this in this final format in terms of the tangent, which is helpful because we started with the tangent. So they converted the tangent into sines and cosines to use the sum and difference formulas that we already had, or the sum formulas, I should say. But then they were able to convert back with a little bit of algebraic manipulation so that our end up result is in tangents, since the function we're starting with is in tangents. It's still not nearly as nice because we have a quotient with a sum in the top and a difference on the bottom. It's not as nice as the sine and cosine identities for sums, but nonetheless, it's a formula and it works. And so they could do the same thing for the difference as they describe in the bottom, and then they get this summary of the sum or difference formulas for tangent. And so it's a formula, and we'll use it in order to evaluate a sum or difference of angles for tangent, like we just did with sine or cosine. All right, so let's now look at some of their examples to help us go through this stuff. Find the exact value of sine of 75 degrees. So I just did 15 degrees, which was the difference between the 45 and the 30. And they're doing 75 degrees, which is the sum of the 45 and the 30. So this will almost look the same as what I did. But what will end up happening is they'll end up with a plus in the middle of their answer, whereas I ended up with a minus, but everything else was the same as the example that I did in the beginning. So hopefully that kind of looks like one that we've already did. But again, you had to recognize that 75 degrees is not one of the angles that we're real familiar with, but could be written as a sum of two angles that we are. Doing the same thing with a radian measurement like we did with the cosine in the last session. And now they've also switched from the sine to the tangent. And so what I did last time, because sometimes students get hung up on this, is when you are asked to get the exact value of an angle in a trig function that is not one of the friendly angles that we've worked with before, you ask yourself, well, can I express this angle as a sum or difference of friendly angles that we've worked with before? And the way to help yourself figure that out is to remember that our friendly angles are pi over 3, pi over 4, pi over 6, and of course you could do pi over 2, which is 90 degrees, things like that. And then what you want to do to see, well, how could I end up with 7 pi over 12, since that's a different denominator, is you convert all the friendly angles we know into the same denominator as the fraction you want to end up with. In this case, to make them all have a denominator of 12. So for pi over 2, I'd multiply the top and the bottom by 6. So I would get 6 pi over 12. If I have in the 3 in the bottom, I'd want to multiply top and the bottom by 4, and I'd get 4 pi over 12, 3 pi over 12, and 2 pi over 12 for each of those friendlier angle measurements that we know about. Then we can look at those and say, how can I use any two of those to get a 7 pi over 12? And then from there, hopefully we'd be able to say, oh, look, I can take the 4 and the 3 pi and add those, and that would give me 7 pi. And that's how they get what they used here. That's how they recognize they could write 7 pi over 12 as pi over 3 plus pi over 4. Pi over 3 plus pi over 4. And then we simply apply the identity. And so we call pi over 3 the A value, we call pi over 4 the B value, and the formula says tan A plus tan B over 1 minus tan A times tan B, and we substitute in our angles that we like. And then we find, we substitute each of those with the values that we know. You could look at a table of values for tangent that includes these common radial measurements. You could also evaluate those directly in a little triangle, for example, making a 30, 60, 90 degree triangle or something like that. So tan of pi over 4 is 1, tan of pi over 3 is root 3, so they're plugging those in. And then when you get that, you end up with something like they have here, just to sort of go through their steps so we can understand what you'd have to do if you're doing the problem. And then what you end up with on the bottom is 1 minus the square root of 3. So we would need to rationalize that denominator. That's a key thing that really has to be done here. And so we want to remember that if you have a radical, like a square root of 3 in this case, in a sum or a difference, and you want to rationalize that, then you have to multiply by what we call the conjugate. And so conjugates are when you have a sum of two things, then the conjugate of that is the difference. And vice versa. If you have a difference of two things, then the sum is the conjugate of that. And the reason we remember these conjugate pairs is when you multiply them together, they give you a difference of squares. And so if either or both of those terms were square roots, then when you get a difference of squares, all the square roots will be squared and go away. So in this case, we had something of the form of a minus b. And so we need to multiply by the conjugate a plus b. So if I have 1 minus radical 3, I turn around and multiply it by 1 plus radical 3, and I end up getting 1 squared minus radical 3 squared, which is just 1 minus 3. And then the root goes away, and you don't have a root in the bottom anymore. Now, of course, if you're going to multiply the bottom by the conjugate, you had to also multiply the top by the conjugate. And so that's where this fraction of 1 plus root 3 on the top and the bottom was introduced. That's done to rationalize the denominator. So we're multiplying by the conjugate on the top and the bottom to rationalize the denominator. So that's me trying to fill in some explanation about what they're doing here. Of course, you can review this video or these slides later to try to think it through on your own instead of having me spoon feed you the rationale and things like that. Then once they've done that, well, in the bottom, as we saw, you end up with 1 minus 3, which they have here, which just simplifies to -2. But in the top, you also have these two binomials that are now no longer conjugates, and you have to FOIL that out. So root 3 times 1 is root 3 times another root 3 is 3, 1 times 1 is 1, and 1 times root 3 is root 3, and that's how they get those 4 things on the numerator, by FOILing out the binomials in the top. Refreshing your algebra process when they taught you this in Algebra 2 or wherever you learned how to do this and then probably forgot it, because it's easy to forget if you don't use it. So then they end up here. And then the final thing to point out is if you do end up with a denominator factor that can be divided into both of the terms in the top after you combine like terms, then you need to simplify further. So they divided 4 by -2 to get -2, and 2 times root 3 divided by -2 is -root 3. And then they end up with this final form of the answer. So when you're working with the tan, sum, or difference identities, often this kind of work becomes necessary. So this is a good example to look at and think about if this was getting stale or you kind of forgot how to do some of this kind of stuff. Because of the fact that the identity itself creates this big fraction where the bottom may have root stuff in it when you take your tangent of angles, then this is a common process we're going to need to go through for this kind of problem. Okay, so let's look at 1C. Find the exact value of sine of 40 degrees times cosine of 160 minus cosine of 40 times sine of 160. And we had an example 1C like this in the previous section when we were looking at the sum difference of cosines. And the thing to recognize here is that this fits the pattern of sine A cosine B minus cosine A sine B, and that is the pattern in the identity for the answer for sine of A minus B. So then you could evaluate this string of these 4 trig functions that are multiplied and subtracted in the end by just replacing all 4 of them, where the A value is 40 degrees and the B value is 160 degrees, by putting those into the sine as a difference. And in this case, after we take that difference, it gives us something that we can evaluate. So when we get sine of minus 120 after taking the difference, notice that they pulled the minus sign out. That's a property of the sine function. That's because the sine function is what we call an odd function. So that allows us to pull a negative out of the argument. If there's a negative in there, just pull it outside front. Cosine is an even function, so if there's a negative in the argument, you could just take it out and throw it away. But for the sine function, you can take it out and put it out front. And then how would we evaluate sine of 120 to get the exact value? I'm going to just remind us that we now want to be able to refer to a circle and think about these things with what we call the reference angle and things like that. So we know we have 90 degrees up top here. We have 180 degrees over here. And so to get to 120, I'm going to go past the 90 degree part. 90 goes past that to get to 120. And how far past that have I gone? I've gone 30 degrees farther than 90. And so that gives me a 30, 60, 90 degree triangle, which I'll draw over on the side here, where this is 30, this is 60. So I'm taking this triangle over here, and that's what we were calling before the reference angle. And remember that this point over here, xy, is going to be where x is the cosine of 120 degrees and y is the sine of 120 degrees. So this y value here will be the value that we want. So sine of 120 degrees will be the y value in this triangle. And when we have a hypotenuse of 1, then the short side is 1/2 and the long side is square root of 3 over 2. And so in this case, the y value, which is that distance of our point, is the square root of 3 over 2. And so they replace sine of 120 degrees with square root of 3 over 2, and there was a minus sign sitting out in front, and that's how they finally got this answer. All right, so cruising along here, let's look at example 2. Writing functions as expressions involving functions of theta. Write each function as an expression involving functions of theta. So when they say functions of theta, they mean instead of having a 30 degrees plus theta inside the function, we want to just have theta inside the function and get the 30 degrees out of the argument and write any of those values separately. And so in the case of 30 degrees plus theta, in the cosine, they went back to our cosine sum identity. Cosine of a plus b is cosine a cosine b minus sine a sine b. So using a as 30 degrees and b now as the theta, well, we're not going to be able to evaluate cosine or sine of theta because we don't know what theta is. But then when we have those, we are expressing the expression then contains functions of theta. So functions of theta will be like sine theta, cosine theta, something like that. And so when we plug those in, we can then evaluate the parts that don't just have theta, like cosine 30 and sine 30, giving us the 1/2 and the root 3 over 2. And then with the common denominator of 2, they end up with this expression where you have square root of 3 cosine theta minus sine theta all over 2. And that is an expression involving functions of theta instead of functions of 30 degrees plus theta. So yes, one of the things we have to get used to in these kinds of problems is that there's really no rhyme or reason for what they're doing. There's no explanation as why we would need this, how this is helpful. It's kind of like practicing using a tool like a screwdriver or a hammer without actually doing any project. Like you could sit there and practice hammering things and say, well, why would I ever want to bang on something with this hammer? And not really know what project that would be used for. But then if you're actually building something and you're putting in nails or taking something apart with a hammer, then all of a sudden you're glad you know how to use the tool. And it's worth mentioning that here because you really kind of have to just do what they say to do. And that means you have to understand what the instructions are and then just do that. Write each function as an expression involving functions of theta. And what we started with involved something more complicated than theta. Theta plus 30 in this case. So they do the same thing here, and we look at it with the tangent of 45 degrees minus theta. And if we plug that in to the difference of angles for the tangent identity, it's very nice because tan of 45 degrees is just 1. And so every place where you ended up with a tan of 45 degrees, you get a 1, and that all simplifies down to this. So in this case, we didn't have to do too much. We didn't have to get a common denominator, and the angles came out nice. But the key thing is what they asked us was that instead of having a function that's just about theta, we had a function that involved theta subtracted from another angle. And so we were able to write that as an expression that just had functions of theta instead of something more complicated like 45 degrees minus theta. And they do the similar thing for sine of 180 degrees minus theta as well. Okay, so that's example 2. Let's look at example 3. In this case, they're leaving it for us, or maybe they do it on the next slide. Looks like they're going to maybe do it over here. So let's see what the problem states and then see how much of it we want to do before we look at what they did. So finding function values and the quadrant of an angle A plus B. Suppose that A and B are angles in standard position with sine of A equal to 4/5, where A is somewhere between pi over 2 and pi, which means in quadrant 2. And cosine of B is equal to -5/13. And the B angle is between pi and 3 pi over 2, which would mean that it's in quadrant 3. Find each of the following. So how do we do this? Well, first of all, to find sine of A plus B, we do know that we have a formula that would allow us to break this into sines and cosines of A and B. And they've given us exactly what sine of A is and what cosine of B is. So since sine of A plus B has a sine of A and a cosine of A in it, and has a cosine of A and a cosine of B in it, that we have sines and cosines of both A and B in the formula. Having just sine A and just cosine B is not enough. We also need sine of B and cosine of A if we're to apply these formulas and get a value. So in order to do that, we want to use the information provided and see if we can figure this out. And there's a few different ways to do this. But if I know that sine of A is 4/5, which is the first thing we have, we also know that sine squared A plus cosine squared A would be equal to 1. And so if I know sine A, I should be able to figure out cosine A, especially if I know which quadrant A is in. So in this case, that would mean that sine squared A would be 4/5 squared. Cosine squared A is equal to 1, which means that cosine squared A is 1 minus 4/5 squared, which is 16/25. And if I square root both sides and combine these together, I'm going to get that cosine A is the positive or negative square root 1 minus 16/25. 1 is 25/25. Minus 16 would give me 9/25. So cosine A is the positive or negative square root of 9/25, which is 3/5. Now, in order to figure out whether it's the positive or negative of 3/5, we can remind ourselves that angle A for this problem is in quadrant 2. And in quadrant 2, x values are negative. Cosine A is the x value of whatever that point on the unit circle would be for angle A. So that means that for our work, cosine of A for this particular angle would be negative 3/5, because it would be the negative value since it's in quadrant 2. And we're about to do the similar thing to find out what the cosine, what the sine of B would be, what the sine value of the B angle would be, just like we just found the cosine. We just found the cosine, but we also need sine of B. So we'll use cosine of B to figure out sine of B. All right, now I would just do the same thing with cosine B to get sine B, and then I would use all 4 of those actual values to evaluate sine of A plus B. So I could continue here, but let's see if this gives us enough insight to follow along with what they do and see if they do this sort of similar thing here. Yeah, so in this first slide here in their explanation, they came up with the solution that I just got for cosine A, which was, that was negative 3/5. And then let's see if they then turned around and found sine of B. They did. And so then when they did the same thing and found sine of B, they got this value for sine B. And then when you know all 4 of those, when you know sine A, sine B, cosine A, cosine B, well, then you can figure out all of these. Because sine of A plus B will involve those 4 things. Tan of A plus B involves tan of A and tan of B, but you can write those as sine A over sine B, or cosine, sine A over cosine A, or sine B over cosine B, which you know all of those. So once they've gotten that, then they say, oh, well, all right, well, then we can find tan of A by writing it as sine A over cosine A, and we know both of those, so we just make the fraction and simplify, and we get the answer for tan A. Similarly, we can find tan B by making sine B over cosine B, and when we know tan A and tan B and sine A, sine B, cosine B, we can evaluate everything. So for sine A plus B, they do the formula, plug in the values, and get this answer. And so literally, we now know the sine of A, the cosine of B, the cosine of A, the sine of B, all of those were figured out. And we now know tan A and tan B because we did that as well, and we get that answer. So lastly, they sort of say, well, could we figure out what quadrant the sum of these angles would be? Well, if you know the sine, if you know the sine value of an angle or and the tangent, then you can figure out what quadrant it's in. For example, the fact that the sine of the sum of these angles came out to be positive implies that the y value of the point was positive, because the sine is the y value. So that means you have quadrant 1 or quadrant 2. Those are the quadrants where the sine of the point would be positive, because that's the y value. And then if you look at the fact that the tangent is positive, where is it that the tangent is positive? Well, when the sine and the cosine are either both positive or both negative. So tangent is positive implies that you're in quadrant 1 or quadrant 3. Those are the places where the tangent comes out to be positive. So for the sine of A plus B to be positive and the tangent of A plus B to also be positive, that puts us in a position where we must be in quadrant 1, because that's the quadrant where both of those things are true. Now, they just sort of say from parts A and B, sine of the angle is positive, tan of the angle is also positive, and then they just say the only quadrant in which the values of both sine and tangent are positive is quadrant 1, and so this must be in quadrant 1. So the logic isn't sort of spelled out with each one being thought of individually here, but that's exactly the same logic they used to get the answer here. So we have one more example on this final slide to finish up with today. Verifying an identity using sum and difference identities. So it says verify that this equation is an identity. And this is a kind of a weird looking specific identity that if I have the sine of this sum of angles with pi over 6 and theta, and I add that to the cosine of this other sum of angles with pi over 3 and theta, then in the end, this is all just the same as cosine theta. So this is not a common identity, but it's really a way to practice using these sum identities to manipulate an expression. And really what we would be doing here is taking this more complex thing on the left and recognizing that using the identities, we could simplify it all the way down to just cosine theta on the right. So they take the thing on the left and they apply the sum formula for sine and cosine to just bust it up into all the pieces. And then once we've done that, well, what do? Well, then at this point, we're trying to simplify. And so how are we simplifying? Well, we can evaluate sine of pi over 6. We can evaluate cosine of pi over 6, cosine of pi over 3, sine of pi over 3. And when we evaluate this and you get these 1/2 and root 3 over 2, when they do these evaluations, then they're able to simplify what's left by combining like terms, and it all ended up just adding up to one single cosine theta. So you kind of have to trust in the problem. They're telling you what you're supposed to get in the end. You're going to get cosine theta in the end, and you just have to verify that by following through and doing the work with the sum formulas and manipulating some algebra, evaluating the angles. The big thing is if I have sine of pi over 6 plus theta, well, I don't know what pi over 6 plus theta is, but I can take the sine of pi over 6. I can take the cosine of pi over 6. So by using the sum angles and getting rid of the pi over 6 part and evaluating those parts, you're left just with things in terms of theta, as we saw in the earlier example. And that often allows us to simplify things a lot. And this is a great example of that on the final slide of this. Well, there's a blank slide. I guess that's the final slide. And that's the final example of the section. So use the identities to find the exact value. And again, I have a hard time writing with my mouse, so I'm going to copy this over. So we're looking at tan of negative pi over 12. And we're supposed to find the exact value. So I will point out that as we discussed in last class, when they say the exact value, that's telling you that you're not going to just type this on your calculator and get a decimal, that you're going to have to use some identities to work this into things that we know exact values for. Okay, and here's the problem. So this was a homework problem number 5, or not a homework problem, but a practice problem number 5, where we're supposed to figure out tan of negative pi over 12. And so the key thing for us would be to say, could I get this in terms of a tan of a sum of two angles or a tan of a difference of two angles? And because it's negative, we're kind of expecting that it's going to be with a difference, where the B angle will be larger than the A angle. So when I take the difference, I'm ending up with a negative. And so how would we do this? Well, again, just like I was saying before, take your common angles like pi over 3, pi over 4, and pi over 6, and express them in terms of twelfths so that you can see what combination of those might give you negative pi over 12. And so this would be 4 pi over 12, 3 pi over 12, and 2 pi over 12. And we basically want to do a subtraction where angle B is 1 pi over 12 larger than angle A, so that when I subtract the angle B, I'm left with negative 1 pi over 12. And there's a couple of ways we could do that. We could do 2 pi over 12 minus 3 pi over 12. Or we could do 3 pi over 12 minus 4 pi over 12. So there isn't only one right way to do this. But let's say we decided to let 2 pi over 12 be A and 3 pi over 12 be B. Then A minus B would be 2 pi over 12 minus 3 pi over 12, which would simplify to negative 1 pi over 12. And that's the angle we're trying to evaluate here. So, and of course, 2 pi over 12 is the same as pi over 6. And 3 pi over 12 is the same as pi over 4. So that means I'm going to write this as the tangent of pi over 6 minus pi over 4. And if I take pi over 6 and minus pi over 4 and I get a common denominator, I end up with negative pi over 12. So that's why I can replace negative pi over 12 with that difference. So then I would use the formula for tan of a difference, which I have right up here. Oops, a little bit farther back. A lot farther back. And I'm getting blurry. There it is. So our formula for the difference is right here. And so you say, okay, tan A minus tan B is tan A minus tan B. Tan of A minus B is tan A minus tan B over 1 plus tan A tan B. So the minus is in the top and the plus is in the bottom. So in this case, I would have tan A is pi over 6 minus tan B is pi over 4 over 1 plus tan A, which is tan of pi over 6 times tan B, tan of pi over 4. Questions about how I was able to convert tan of negative pi over 12 into a tan of a difference and then use the formula to get something to evaluate here? All right, so we need to evaluate these. Well, pi over 4 is the angle where sine and cosine are the same thing. And that usually ends up being easier for us to remember that therefore tan of pi over 4 is 1. So that tan of pi over 4 is a 1, and this tan of pi over 4 is a 1. Tan of pi over 6. So pi over 6 is the same as 30 degrees. So if I want to recreate this to myself again, I can make a 30, 60, 90, where I have 1/2 over here, root 3 over 2 over here, and I got a 1. And so if I take tan of pi over 6, tan of 30 degrees, it's opposite over adjacent, sine over cosine, opposite over adjacent. So that's 1/2 over the square root of 3 over 2, which is 1 over the square root of 3. Or if I want to rationalize the denominator right away, it's root 3 over 3. So this is going to be square root of 3 over 3. And this is going to be square root of 3 over 3. So what do I end up with here? Let's see if I can do that. So I'm going to get the square root of 3 over 3 minus 1 divided by 1 plus the square root of 3 times 1. which would be square root of 3 over 3 times 1, which is square root of 3 over 3. And now we still have to play with this to simplify it. So first of all, I have these little baby fractions, these little fractions inside the big fraction. So I would clear those by multiplying the top and the bottom by their common denominator. If I multiply everything in the top and the bottom by a 3, root 3 over 3, the 3's cancel, and I get square root of 3 minus 1 times 3. And then on the bottom, 3 times 1 is 3. And again, the root 3 over 3, the 3's cancel, and I get root 3. And now I have a radical in the bottom, so I need to rationalize the denominator, all of this fun algebra coming back to roost. So I'm going to multiply by the conjugate in the top and the bottom of the bottom, because I'm trying to get a difference of squares in the bottom. So that's going to be, well, actually, the difference doesn't matter. So on the bottom, let's say I had the square root of 3 plus 3. Since a sum can be reversed, then the conjugate would be the square root of 3 minus 3. So I'm going to multiply by square root of 3 minus 3 in the top and the bottom. And I reverse them just because then we can see that in the top, you have the exact same thing times itself. So if I have 3 squared minus the square root of 3 squared, which is the a squared plus b squared pattern in the bottom, I'm going to get 9 minus 3, which is 6. So I'm going to get the square root of 3 minus 3 times itself in the top divided by 6. Now, I actually don't know if they want you to FOIL out the top or not in the homework problem. You could FOIL it out, or you could maybe just leave it like that. So let's find out by me going back and seeing if I put this in this format, if it doesn't like it, or if there were instructions that I just ignored that told me how they want me to form my answer, or maybe they'll just mark it wrong because I did something wrong in my. So simplify your answer, including any radicals. Use integers or fractions for any numbers in the expression. All right, so let's see if it takes what I came up with. And I have some hope that I have the right answer, but we will see. So I'm going to make a fraction. The bottom of the fraction was a 6. Let's see, there we go. And then in the top of the fraction, I'm going to do some parentheses. And then I'm going to do the square root of 3 minus 1, no, minus 3, close parentheses, squared. All right, see what it says. All right, so I guess they don't like that format. It was worth trying it out. Let's see, express the
Professor,
angle. Yeah.
Oh, wasn't it like minus 6? Like,
Was the 6 minus on the bottom? I had 3 minus 3. Oh, you're absolutely right. I reversed it. I'm dyslexic, so I often reverse things. So let's see, on the bottom, we had square root of 3 plus 3, square root of 3 minus 3. And then when I wrote it on the left, I had 3 squared minus root 3 squared. Yeah, so maybe it's just the minus sign. Let's see if that'll fix it. Thank you. Because I do want to see if it'll take it in this format. No, it still doesn't like this, I don't think. Oh, now here we're giving a different hint. That's good to see. Although your answer is equal to the correct answer, it's not in the correct form. And be sure to read instructions. All right, so what in the instructions are saying that they want me to FOIL this out? Radicals, integers, fractions. I don't see what they're saying that wants me to FOIL that out. But let's say we FOIL it out. If I FOIL out the top, oh, it's because if we FOIL it out, we can then combine some like terms. So that's why they want us to do it. Yeah, that's fair. I think if we FOIL this out, we'll be able to combine some like terms. Got about a minute left, so let's take a look. If I FOIL this out, I'm going to get the square root of 3 squared minus 6 times radical 3 plus 9. Yeah, so that makes sense, the reason they want, because we can simplify that further. So square root of 3 squared is 3. 3 plus 9 is 12. So I'm actually going to have 12 minus 6 root 3. Yeah, there's quite a bit of simplification we do here. So we do need to FOIL that out. That's divided by minus 6. And that's just going to go down to being √3 minus 2. Oh yeah, that's way better. So that's a definitely reason why we wouldn't want to leave it all unfinished like this. So let's take all of this out and do square root of 3 minus 2. It is nice that they told us that we had the correct answer, but just not in the best format. So that is very important and helpful. And 1:45, good timing.